Welcome to my Commodore 64 Games memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Bubble Bobble, published in 1987 by Firebird. Copyright Tato, and the developer was Software Creations. The coder was Stephen Ruddy, and graphics and title screen were by Andrew Threlfall, and the musician was Peter Clark. I'm going to start off in C64 Debug GUI, and it's worth noting at this point that the disk version that I have uses the GMA87 protection method, commonly called Bleep load, because, as you can hear, it goes bleep. It's by Graham Ashton, who also did the disk turbo loader, and I had a video about this, and I went into quite some detail about trying to find all of the different versions of the disk turbo loader and the protection and stuff like that. And I'll add a link to that video in the description below. So I really loved this game. It was a really good conversion. I think it was a really good conversion of Bubble Bobble. Considering how difficult it would have been to get Bubble Bobble properly ported over, I think it was a really good job. I'm looking at this screen here in C64 Debug GUI because I want to see exactly where the real sprites are and where the not hardware sprites are. In other words, software sprites. Now this game is really unusual because it makes heavy use of software sprites. These software sprites are usually used for the bubbles, but they're also used for a couple of other effects as well. In the game, it uses basically software masking to update the character sets that are used for the level. The levels are actually quite simple, so the game can actually get away with it by updating the character sets mostly for the bubbles and some of the other effects that go on as well with character set masking. But here we can definitely see the player character and the monsters are hardware sprites because of the red bounding box, and then we have the bubbles, which look and move like sprites, but they're not hardware sprites, they are software sprites, and they will be updating the character set data. When the player character comes in, note that it is using a 2x2 sprite grid, and when the get ready message comes on the screen, note that actually it's using masked characters. There's no red bounding box. And this is basically the game. You jump around the platforms. There is no real scrolling during the actual gameplay itself. There's some scrolling between the level transitions, but that doesn't really have all of these bubbles and everything like that going on in the background, so the game doesn't need to worry about scrolling the screen. It doesn't need to spend a lot of time updating the screen character-based graphics. You see, that hurry up message was actually masked characters coming in. It wasn't hardware sprites. Anyway, so the game doesn't need to spend a lot of time scrolling screen data, so it can afford to dedicate a lot of time to updating the software sprites. And that's not a surprise, because actually you can shoot quite a lot of bubbles, and there can be quite a lot of bubbles in one horizontal band, and they don't interfere with the 8 hardware sprites in a horizontal band restriction that is actually inside the Commodore 64's hardware. If I bring the character set view up in the top left hand corner here and then blow some bubbles, blowing bubbles, right? You can see that the character set data actually has the bubble characters updated into roughly the middle towards the end of the character set there. The more bubbles I blow, or shoot rather, whatever, the more character set entries get updated. I can see a round 3 ready message with the masked characters eventually get overridden there as well by more bubble based characters. The trapped enemies, when they look like they're inside bubbles, are still using hardware sprites. It looks like the game kind of permanently has an allocated maximum number of hardware sprites, which is 8, and then it has a maximum number of 6 enemies on the screen at the same time. So if the enemies turn into what look like bubbles, it still reuses the same hardware sprite for that enemy. It just changes the frame. It's worth noting that the screen and also the character set as well, if I unlock the character set here on the right hand side, we can see that the character set switches between these two character sets and also switches between these two double buffered screens. So depending on the screen data and depending on the character set which is visible, then we can see different frames, or two different double buffered frames from the game. Let's look at this more in detail with ICU C64. Rearranging the debug windows and looking at sprites in memory, we can see that there's a whole bunch of sprites in the second bank which is being used here. So ICU 64 lets me see the whole range of sprites for a whole bank, and actually I can open up multiple windows and see all of the sprites simultaneously. But here we can see that there's a very large sprite grid being used for probably the end of game boss or whatever it is, but I'm not going to play the game to see that. But we can see quite a lot of variation in the monster sprites. But even though the game is not scrolling, we can see that there's quite a lot of memory updates, the green writing memory updates in the debug memory view there. Now if I'm pausing the game using the emulator here and then advancing each frame, we can see that actually the game doesn't update everything on every single frame. It was updating the bubbles every 2 or 3 frames, and it was updating the enemies every 2 or 3 frames or something like that. So let's have a look at the character set debug view. Now I'm zooming in the window here and reorganizing it so it makes it easier to see. But basically I'm looking at 2 character sets which have a duplication of characters across them. However, that's only for the first, looks like maybe 48 characters, maybe 64 characters. So we've got some letters and numbers, and we've got the characters used for the background. But we seem to have different updates for the double buffered bubbles for the software sprites. We can see here that the frames are not synchronized across both character sets, and that's no surprise because as it's displaying one screen with one character set, it's updating the character set data and the characters in the screen for the off-screen view. So I don't know if you can see that, but basically when the bubbles start floating up through the levels, we can clearly see that the bubble characters include things like level data background characters and stuff like that too. So we can see exactly where all of these green memory writes in the memory debug view there are going. The green memory writes are mostly going into updating the bytes used for the character set data. Don't forget that each character that's displayed on the screen uses 8 bytes for its character set data. It also uses 1 byte for the character screen and another byte which is in a different part of memory for the color screen. So I've got a crazy idea that I want to understand this software sprites drawing method in more detail. So I think we're going to have a look at the code. But you can clearly see here in this debug view that the bubbles are definitely character based, because in the top right hand corner there with the 2 screens side by side, you can definitely see that the bubbles are appearing in the text screen graphics map debug window. When the round starts, look at the ready message in the middle of the screen, and you'll also see that it is masking the white text with the level background as well. And of course that appears in the character set. I'm opening the Vice emulator monitor window here so that I can start adding some watch points or breakpoints in code, or watch points for memory, so we know where the two character sets are. I want to try and identify a good memory range for where the dynamic characters definitions are being updated to, especially for the bubbles. So I'm looking to use the fill command here to fill the character set data with 0, and then I'm looking to see what's changed in the character set, so then I can identify a good memory range for this. I suppose I could count the characters, but I'll just use the fill command because it's immediately visually obvious about how much memory I'm filling and what that memory address range is. I can make a reasonable guess about where this data is going to start. So let's try this range. I'm going to save a snapshot first, actually. I don't really want to get back to the same position in the game without having a snapshot, just in case I make a mistake or screw something up. So I think that actually obliterated some of the characters used for the score panel, which is a bit of a whoops. So the score panel is now flickering for one of the character sets. The score panel graphics weren't obliterated for the other character sets, so that's why it flickers. But at least you can see how frequently the game screen updates. It wasn't every frame, right? It was every 2 or 3 frames. That looks like a slightly more sensible memory range. Okay, I'm getting there. That's the second character set. So you can see once the bubbles with the letters on them start coming up, they also get updated into the dynamic character set data. So now I have what looks like a reasonable memory range for the dynamic characters, for the software sprite animations. I think we can add a watch point to see which code is updating that memory, right? Now this is a really powerful part of the emulator's monitor because it gives you a nice hardware on read or write memory breakpoint, which is a really powerful debugging feature. It certainly makes my life easier when I'm trying to understand other people's code. The thought just came to me that if it is updating the characters and the character set data, then it's going to have like an off-screen buffer of the original game, or some kind of buffer where it stores the data. And I was looking through the memory and I found these two screens here at roughly 8400 and 8C00, but they're not exactly aligned. They seem to be a page different. So that's why the graphics map view is not displaying them entirely correctly or aligned with how you would normally expect. But it seems to be that this area here that I'm waving the mouse around over seems to be the original character set data for the displayed level, so that when the bubble remove code is executed, it can just copy across from a pristine, unchanged source. This seems to be the original data for the score panel, right? Actually, doesn't seem to be part of the level. But if I use the screen editor functionality here to edit this data in memory, and then I shoot some bubbles over that area that I've just updated with extra characters, you can see that it's restoring the characters that I put in the backup there, so that's why I've got those horizontal grey lines. When the level transitions from this screen to starting the next level, it's worth noting that we have some dynamic characters for the level-based platforms and also some of the pickups as well, I think, or power-ups that are going to be expected to be found in the game, which is interesting. It means that when the game progresses between level, it's actually updating the dynamic characters as well. If I put a whole bunch of extra characters now, the P characters, in this off-screen backup, we can see that when I fire the bubbles now, when the bubbles remove or animate, it's restoring the background character that was in the off-screen backup. However, you'll note that I can float down through and it doesn't stop me walking over what should be solid characters. So there's obviously different data being used for the actual level collision compared to what is visible. This is different, I think, to how the Creatures game did it, because Creatures was actually performing collision detection on the visible characters buffer. It didn't have a separate collision screen buffer. And if you look here, this screen data above, which is again not aligned to the screen data alignment normally that you would normally expect to see, I can see this pattern here. So if I paint over with the inverse at character, then I can stand in the middle of the air where there's no visible platform. So that's useful to know, is that screen data there, which is not aligned, so it looks misaligned in the graphics debug view, that data there is actually the collision data for the level. Having a quick squiz through the memory, I can see that there's some text in memory as well, but that's just the data, that's just the progress messages, and I think maybe the game win message. Anyway, so I can pretty much see that the range in that character set data from 4B00 to 4, well, basically 4FFF, right, which is the last character, it's all being used for dynamic sprites. During the game, it's practically safe to delete all of that data in memory because the game is continuously refreshing character set data into that place in memory. So that's cool, that's useful to know. It means that the software sprite rendering is refreshing the whole memory. It's not doing some kind of like previous frame caching methodology, which of course it could do, but it's not. So that's useful to know because it means that we're looking for a particular kind of shape or functionality of a routine. So this is going to be useful to know when we're actually debugging the code. I think I can count a maximum of what looks like 12, 13, maybe 14 bubbles, 15. If I stand there shooting or blowing these bubbles going up the screen, before the bubbles expire, you see the bubbles flash and eventually expire. So this again tells me the kind of scope or behavior of the routine, of the software sprite animation routine that I'm looking for. I'm looking for something which is updating at least 12, 13, 14, 15, 16 sprites perhaps, maybe even 17 or 18. We'll see when we actually get deeper into the code. Now to actually find the code, we're going to use a watch breakpoint on memory. So let's put a watch breakpoint just for storing. We don't care about reads as such. This is during the game execution as well, so it's not actually, it didn't clear the data anyway from the title screen through to the level transition to actually displaying the first frame of the level data anyway. So, oh well, look at this. Well, this is great. This is pretty much obvious code here. We've got a semi-unrolled loop where it's doing load and or store with 3 or 4 different parts of memory. In other words, it's 4 different addresses, right? A load indirect with 3.1, and then an AND with an absolute address, an OR with an absolute address, and then a store indirective with a different 0-page location. So that looks like that was the code updating the character set data. Well, it was reading this area of memory, which looks like multicolor animation frames for software sprite-based data, doesn't it? It looks like there's some other data mingled in there, but basically that data looks like sprite data for the software sprites. In the other bank, it doesn't have to be in the Visible's Vic bank because it's copying it from somewhere else in RAM. It doesn't matter if it's visible or not to the Vic. Don't forget that the VIC chip is only able to really view 16 kilobytes at a time unless you use fancier raster-based effects for changing which bank is visible. So this routine definitely starts triggering only when bubbles are being updated on the screen, or when other sprite-based graphics are coming on the screen too. So there we go. There's no breakpoint triggering when there's no bubbles animating. And these ones here. Yeah, oh look. Okay, so I picked up the pickup and it started drawing. It has started drawing these diamonds. We can see the diamonds start getting drawn in the debug view there in the graphics map. So although they look like diamonds in the debug graphics map, when they come on screen they actually fade on with kind of like a reverse dissolve effect into rainbows. So obviously the character set which is being used is static. It's not changing at this particular point in time. But the graphics map debug view is rendering the screen data with a different character set. So that's interesting. When this bonus pickup screen comes on, there's no double buffering going on of the character set data, and no double buffering of the screen data either. It's just a single static screen buffer with a static character set. Okay, that's interesting to note. It means actually that explains why these bonus pickup screens don't have any bubbles. Look, well, I think this is the end of the level. Oh no, the end of the level usually does show bubbles, right? So yeah, I mean the bubbles don't animate. There are no bubbles on these bonus pickup screens, so that explains that strange occurrence. Anyway, I always wondered why the bubbles weren't displaying when the bonus pickup level was being displayed. So anyway, going back to the code, this is the ranged breakpoint for the software sprite animation update routine. Load and or store basically loads the original character set data. It then ANDs with what is probably a logical bit mask for punching a hole for the outline or the silhouette of the intended software sprite. And then it does an OR of the software sprite data itself, and then it stores into a new memory address here. So we can see that in 3132 indirected, it's actually reading a character from 4900 in memory, and then it stores it into a different area in memory, which is at 3A or 1A, for example, or 1A. All of these indirected memory addresses here are pointing to slightly different areas. Bear with me for a second, I'm just updating my debugging notes text file. This text file will be committed to source control, and I will share the link in the video description below to where you can find this file in source control. It contains my thoughts and some debugging notes as well, so that you can look through this back later on and you can find out what I found out. So while it's great that the memory-based watch point triggered the debugger here, I actually want to trace back through this code and understand it in a lot more detail. So I'm having a look back through the disassembly now to see if I can find roughly where the draw routine starts. What I'm looking for is that I'm looking for a previous RTS, which is a return from subroutine, which would mark the end of the previous subroutine in memory, or I'm looking for a jump or something like that, which would be a natural break between two different routines. What is interesting to me is that this routine at E82F seems to loop around for a value of updates in the 0-page memory location 3D in hex there, but it's just doing optimize load and stores, which is loading from the source data, loading from the sprite data and then storing it into the new character set data for that software sprite. It's not doing an and it's not doing an or. And I think this is for sprite data or software sprite data, which obliterates the entire pixel row. So there doesn't need to be a mask. It knows that it can optimize out the masking process because the mask will always remove existing data in the character set. So it just copies it over straight away without needing to do a mask, which is an interesting way of optimizing this routine. I'm not too sure how much time that would really save, but anyway, I guess it was worthwhile. You have to, the routine would have to store some extra range information, which I think goes into that 3D 0-page memory location there, which basically says, I want to optimally copy this many number of bytes, and then anything outside of that range I want to do the mask test with. I think that's probably what it's doing. This load Y at E82D there with the hardware breakpoint for the execution that it's stopped on now seems to be the start of the update loop, but there's going to be calculation done before the update loop for the software sprite, right? The optimized memory masking or copying needs to have some setup code executed to be able to understand what to copy from where and how. So I'm looking for that start address now of the code which starts drawing at least one software sprite. So I'm using the CHIS, the CPU history command, to look at the CPU execution history in the Vice Monitor debugger window here before it starts doing this data masking for the software sprite. So I can see here that actually it's going quite a far way back in terms of execution. There seems to be quite a lot of data setup being done before it actually starts drawing the sprite data. That breakpoint didn't trigger. I think I got the wrong entry point there. Let's go back to the memory address that we know is good for a breakpoint. The number of times I use the shortened command in this old version of Vice when it doesn't support it. My memory. Anyway, looking back through the CPU execution history, well, that's no good. I can see that there's an I there, which tells me that it was in the middle of an interrupt and returning from that, so I'm going to discount that one. Let's go to the next sprite and see what the execution history is. Okay, well, it's going to all the way to E7B1. Let's put a break at E7B1 and see what happens. And we'll just use the CPU history command again to go backwards and backwards until we get to what looks like a suspicious... look, there's an indirected jump at 0410, which goes to E779. So this seems to be a good place for the start of most of the software sprite draws. I'm guessing that the code above triggers in some other drawing, other different software sprite-based drawing, which just didn't appear on screen at that particular point in time. So I'm guessing that indirected jump obviously updates something different or something special for other things. So we'll go for the testable case, which is whatever is on screen at this particular point in time, and we'll put a breakpoint there. Let's see what happens when I advance the code for each breakpoint trigger. Watch the debug views in the top right hand corner of the screen there. Let's see what happens, and I think we can see that it's updating. Okay, so this seems to trigger once for every software sprite that's being rendered on the screen. Look, so I'm pressing X to continue the execution until it hits this breakpoint next, and it seems to be triggering once for every software-based sprite. Let's see if I can make that clearer. Let's alter these screen views here so that the two double buffered screens are going to be using the correct character set. So the screen in the first screen at 5000 can use that character set because that one looks correct. And then I'm going to create the screen view just for the second screen, which is at 5400, but we need to know which character set to use, and I think it's that character set. So let's first of all scroll this screen over. There we go. That's still screen 5400. I've just panned it over. Then I'm reducing the graphics map debug view there so that it only views the correct screen with the correct character set. Now let's advance for each trigger of this software sprite draw, and yeah, look, if I advance it now, it's drawn 1, 2, 3, 4, 5 software sprites. I'm just making sure which character set it is. Yeah, it's the correct character set, right? Yeah, I'm pretty sure that that's the correct character set. So let's put the character sets back to how they should be. That screen uses that character set. This screen uses that character set. Let's shrink the windows so we don't get confused, and I don't get confused because that was confusing. Right, there we go. Let's put it back again. So each breakpoint trigger now should render one extra sprite, and a software-based sprite, and it is. That's great, isn't it? It's rendering the next frame, so don't forget that it's not going to be match what is visible in the Vice emulator view, of course. Right. So this routine is triggering every single software sprite draw. Let's update the notes to take that into account. Advancing every breakpoint now using the X command, I can see in the top right hand corner there that the software based sprites are being rendered one at a time into the new data. Then it clears what's previously visible and it flips the screen over, you see. And then I advance each breakpoint now, and then now it's rendering the new sprites. The sprite that's up at the top is actually flashing on and off on alternate frames. So then the next screen, when it is visible, because it hasn't quite finished calculating the screen yet, but the Vice screen is going to show the updated positions for the sprites. Once I start advancing this, I should expect to see a sprite. There we go, and I can expect to see the sprite. The next frame that comes along, you see, actually should start displaying a little pop animation. And then I update to the next frame, and then the pop animation is displayed on screen. So that's great as far as it goes, but you know the real breakpoint should be on this indirected jump, right? Because the indirected jump could be going to different sprite draw routines, software sprite draw routines. So we need to have a breakpoint here and then understand this code. So what is this code doing? Let's have a look at the CPU execution history using the chis command again. The chis command? Chis, whatever. Anyway, so this seems to be, once it does the sprite data, the software sprite data copy there, the load store in the CPU execution history, it's using a jump to E96F to get back to an outer loop. It's actually not doing an RTS. It's not doing a return from subroutine. It's just jumping straight back again. It knows where it has to return back to. It doesn't need to have a JSR and RTS to get there. And don't forget that it used an indirected jump. It didn't use an indirected JSR. There isn't one. There isn't a JSR, an indirected JSR instruction. There's only indirected jump. So that's why it doesn't use an RTS. This routine here at E96F seems to be the parent routine, which is doing some calculation on the sprites to draw. There's a little decrement X and a branch on plus to E931 there. So I think E931 is probably the start of the software sprite draw routine, which loops through all of the software sprites to draw. There is a jump there as well. I'm just looking for the real start of this routine. That looks interesting to me. just trying to understand the flow of this code, you see. E96F, I'm looking for the execution address of the routine before. E931, there we go, E931, yeah, that's where it was branching on plussing back to, right? So if I put a breakpoint there at E931, we'll be able to see the CPU execution history. Right, let's put a breakpoint there just to really be on the safe side, I think, and run this routine. There's the decrement X and then the following branch on plus to E931. This goes back to the very beginning again. That seems to be testing. Oh, look, load accumulator CA, X, and then, look, there's a branch on minus and it's a whole table. So if the number is minus in this CA table, it seems to be no sprite, no software sprite, and then we seem to have sprite ID, frame numbers or sprite type numbers, or maybe a combination of frame and type, perhaps. This looks like a typical, kind of like an animation routine with draw functionality or render functionality mixed in with it, right? So yeah, FF is a negative number. That's why we have the branch on minus there at E933. These positive numbers seem to correspond to the types of bubbles that are being rendered, or the bubbles animation frame. We've got 4 normal bubbles at 4, 4, 4, and 4, but then we have a 1E, which is probably the burst animation for the bubble, right? Or the burst animation frame for the bubble. CA looks like the animation frame for the software sprite. There's also a load there at DC, X and EE, X. I'm willing to bet, based on the structure of this code, that that is an X position and Y position at DC and EE and 0 page, those locations there. And just looking at that code, looking at the structure of code, that seems to be particularly obvious to me. It's the most logical, reasonable explanation. If I have a look at the bytes at EE, for example, I can see that the range of numbers, my brain is not working properly, right, the range of numbers there seem to indicate a Y position, because if I looked at DC, the numbers there seem to be all in the same X position, apart from A, which is the offset exploding bubble, right? So I'm willing at this point to put labels for those addresses that correspond to software sprite animation frame, and then the X position and Y position. Going up through the disassembly, I can see that it's doing a load X with $11 that I've highlighted there in red for the breakpoint. That load X with 11 seems to indicate that there are a maximum of 17, but 0 based counting, so 18, 0 to 11 in hex inclusive, which is 18 software sprites in total. If I put a 4 in the beginning of the animation frame address, and also if I put 4 into the, do I want to put 4 into the X position? And I don't know, let's put a suitable number, let's put 16, which is 10 in hex. I should expect to see an extra software sprite being rendered there, right? As it's going to render the next screen, maybe on the other screen, which is currently clear. Oh, look, there we go, it's immediately appeared. Hey, so that tells me that my initial guess was completely correct. Successfully put a new sprite into the software sprite drawer for Bubble Bobble. So I think, you know, that kind of like indicates that this routine is quite easy to understand. And now if I advance the frames a couple of frames, we can see that the new bubble appears in the game view as well. It seems to maintain that state. It's not copying data into the animation table for the software sprite based render from somewhere else. It's actually maintaining it over several frames, look, and actually the new bubble that I added is animating and bobbling up and down and moving around as well, and it has also expired. So there we go, that's cool, isn't it? Wow, fantastic. That's really quite worth knowing how that works. So to really prove a point, let's try adding more than one sprite at a time. So let's put in multiple copies, 5 extra software sprites. Okay, we'll put different positions in so that we can see them. So we'll put different numbers in for the that was the X position, right? And then the Y position, we'll just put different values in as well. 5 values, 1, 2, 3, 4, 5, 1, 2, 3. Yep, cool. Right, so there we are. Wow, a whole bunch of extra software sprites suddenly appear. Bubbles in this case. Interesting, look. The player character is not interacting with the software sprites that I added. That's probably indicating that the game doesn't realize that they should be interactable with. It's probably telling me that the game has some kind of like bounding box check for where it thinks the bubbles are compared to where the animation routine or the software sprite animation and draw routine thinks the graphics are. I bet, you know, the real bubble bounding box information probably doesn't bother to update bubbles which are not active, for example, into this software-based software sprite animation and rendering information right into those tables. So that's probably why. I've made it crash. Yeah, okay. Doesn't seem to like certain values being put into there. But that's cool. Anyway, so this is Bubble Bobble with software and hardware based sprites, and the code for the software sprite draw has now been understood. So that's what I really wanted to do in this video, is to show how the software based rendering works, and to understand the code and to document these code findings so that if anybody else finds this interesting, then I hope they do. If you like watching these kind of deep technical dives into Commodore 64 retro games, then please do consider liking or subscribing to my channel, and a super thanks is also very much appreciated. And thank you very much to the supporters of this channel for sending me super thanks and also itch donations as well. Those are all very well appreciated, and it really does help keep me motivated for creating new content. Thank you very much for watching. Take care, have a great day, wherever you are.